Today we're going to talk about calculating pH. First we're going to calculate pH for strong acids, and you might think this is pretty easy because it's just an equation, and it usually is. Go ahead and pause the video and write your equation for pH. So you should have said pH. P is a mathematical operation. H stands for hydrogen ions, so it's equal to the negative log of the H plus ion concentration. Or, since H plus in real life gets together with H2O and forms H3O plus, it does not just float around as H plus. It's more accurate to say H3O plus, even though most people will not write it like that because it's longer. So, it's important when you're doing these that you consider all sources of H plus or hydronium. Usually there will be one major source that makes solving the pH equation easy, but not always. Sometimes you have to add two together. Here's an example. Calculate the pH of 0.10 molar HCl. Go ahead and pause the video and write down all the sources of H plus in that 0.10 molar solution of HCl. So the obvious one is the HCl. So HCl, when you put it in water, falls apart and it forms H plus, which reacts with the water to make H3O plus, and Cl minus. So there's one source, is your HCl. If you just write the equation like this, HCl falls apart into H plus plus Cl minus, that's fine. It's not what's really happening in real life, but it's an easy way to show the same thing. There's another source too, though. That's the autoionization of water. That 2H2O forms H3O plus and hydroxide. That always happens to a certain extent. Kw is 10 to the negative 14th. Whereas K for HCl is just very large. You can't even calculate it because it falls apart pretty much totally. So, our first source is HCl, our second source is H2O, and we obviously have a main source here. The main source is our HCl. So now that we have our main source, which is millions of times more important than our secondary source, we're going to just do our calculation. We know that we have 0.10 moles per liter HCl, and our mole ratio is just 1 to 1. So that means that we have 0.10 molar H plus or hydronium in our solution. So then we just use our pH equation, take the negative log of 0.10 molar, which is 10 to the negative 1 molar, and so I can find that the pH is 1. Let's do another example. Calculate the pH of 1 times 10 to the negative 10th molar HClO4. Well, in this case, we know that there's still several sources of H plus or hydronium. So go ahead and pause the video and think of your sources. So you should have said, again, the strong acid, perchloric acid, strong acid, so it'll break apart all the way. And then you have water also that's breaking apart into hydronium. So two sources of hydronium. In this example, it's a little bit trickier to figure out which one is important, or if both of them are. So, I mean, you can always use both of them if you're not sure. But in this case, we're going to get 10 to the negative 10th. 1 times 10 to the negative 10th, I guess that is the same thing, molar hydronium from our perchloric acid. From this one, Kw is 10 to the negative 14th because each of these are 10 to the negative 7th molar. 10 to the negative 7th molar hydronium and 10 to the negative 7th molar hydroxide. So you can see that actually our main source in this example, because our concentration is so small, is the water. So because that's the main source, this one actually doesn't matter, but if you're not sure about that, you can add it in and try. And so you just find your pH. the negative log of 10 to the negative 7th molar hydronium, or H+, and so the pH is 7, just the same as neutral water. With sig figs, I just realized that should actually be 7.0. So that's how you find the pH of strong acids. You look for the main source, whether it's a strong acid or if it's the water. If the strong acid is less than 10 to the negative 7th molar, then the main source is the water. Otherwise, the main source is the strong acid. Our next section is about the pH of weak acid solutions. These are trickier because they don't separate all the way. Each weak acid separates a different amount. So we will always have to do equilibrium on it with an ice table to find out how much it separates, and then once we know how much H3O plus forms, then we can find the pH. For example, find the pH of a 1 molar solution of hydrofluoric acid. The equilibrium constant for hydrofluoric acid is 7.2 times 10 to the negative 4th. So a good question to ask yourself is, what's in the solution? Well, it's a weak acid. The dissociation of HF is a reactant-favored reaction because our K value is so small. So mostly in the solution is HF, which separates a little bit into H+, and H2O, which separates a little bit into H+. So we want to know which one is a bigger source, or do we have to add both of them together? So just like we did in the previous example, we're going to compare them. In the previous example, we had concentrations. We had 1 times 10 to the negative 10th molar versus 10 to the negative 7th molar. In this example, we have K values. So you can compare one or the other, but a common mistake students make is they compare a concentration to 10 to the negative 14th for water. You can't do that. Concentration is concentration. 10 to the negative 14th is a KW for water, so compare K values in this case. So HF has a K value of 7.2 times 10 to the negative 4th, and H2O has a K value of 1 times 10 to the negative 14th. So our K value for HF is much bigger and much more important. So that is going to be our main source of H+ in this example. If you're not sure, you can always do both of them, add it together, but it's just a bunch of extra work. It won't change your results at all. So we're going to ignore the contribution of water, and we're going to figure out how much H plus HF makes. So here is my equation. I prefer to write the H2O's, but you don't have to. If you write H2O, it's H3O plus that it forms. If you don't, it's H plus that it forms. And our conjugate base. So our ice table, our initial concentration of HF is 1 molar. H2O is a liquid. It doesn't go in our ice table. It doesn't go in the equilibrium expression. We're not starting with any of these. We want to know how much does it form. So our change is going to be minus X, nothing for H2O, plus X and plus X. And our equilibrium is going to be 1 minus X, X, and X. And you'll notice that what we're trying to find in this problem is H3O plus concentration. It's just X. So if we find X, then we take the negative log of that, and we have our pH. So go ahead and pause the recording and solve for X and solve for the pH. So when I solve for X by setting K, 7.2 times 10 to the negative 4th, equal to X squared over 1 minus X, I'm finding the intersection, I find that X is equal to 2.7 times 10 to the negative 2nd molar H+. So then I take the negative log of X, which is my H+ concentration, and I find that the pH is 1.57. For our next example, let's calculate the pH of a 0.100 molar HOCl solution with a Ka of 3.5 times 10 to the negative 8th, and it's mixed with a 0.100 molar HCN solution that has a Ka of 6.2 times 10 to the negative 10th. So, what you should ask yourself is, what's in the solution? What's the main source of H plus in this problem? Or is there more than one main source? Go ahead and figure that out. So we have Ka values, so we should be comparing those. We have 3.5 times 10 to the negative 8th, 6.2 times 10 to the negative 10th. Remember, there's also water in there. Kw is 1 times 10 to the negative 14th. So clearly that's not our main source. And our water, our cyanic acid is not our main source. It's 100 times less. And remember, it takes like a tenfold change in concentration of H plus for pH to change at all, pretty much. So this is enough to ignore it. If you're not sure whether to ignore something, you can always do both, though. Okay, so this is our main source, is our hypochlorous acid. So go ahead and make your ice table and find the concentration of H plus that hypochlorous acid produces. So when you set up your ice table and solve for x, you should get that x is equal to the hydronium ion concentration, which is equal to 5.9 times 10 to the negative 5th. I'll just mention here that because x is so small, you can actually ignore this x right here, and it makes the equation really easy to solve even without graphing. And you can do that as long as your k value is pretty small. But if it starts getting like negative third, negative fourth, bigger like that, it's not going to work out for you. You can always solve it by graphing though. So I would just say do that all the time if you want. So take the negative log of that, and you find out that the pH for this problem is 4.23. Last for today, let's talk about percent dissociation, which is another way to compare the strength of different acids. So our equilibrium constant, Ka, is one way. Percent dissociation is another way. It says how much does it come apart. So the math equation is just what it sounds like. It's the amount of the acid that breaks apart, the H plus, or you call that hydronium, divided by the initial amount of the weak acid that you had times 100%. So for example, find the percent dissociation of 1 molar acetic acid. The Ka for acetic acid is 1.8 times 10 to the negative 5th. So when we do our ice table, we find out that 1.8 times 10 to the negative 5th is equal to x squared, where x is H3O plus that forms, over 1.00 minus x. And you can graph that, or because this is fairly small of a k value, you can assume that this x is small enough not to matter compared to our pretty large concentration here, and solve it that way. If you do it that way, you should probably check and make sure, is x really small compared to 1 molar? And yes, it is. So when you solve, you find out that x, which is equal to the hydronium concentration, or H plus concentration that forms, is equal to 4.2 times 10 to the negative third molar concentration of H plus. And so when you find your percent dissociation, it's going to be our x value, our H plus, our hydronium value, all over the initial concentration originally before it dissociates at all times 100. So that is going to be 0.42% dissociation. And weak acids are like that. They have a really low percent dissociation. And acetic acid, vinegar, is even not one of the weakest ones. I'll mention here, and you can test it with your calculations if you want, that the more dilute a weak acid is, the more it will separate. It has more water around it that can start breaking it apart instead of being with other acetic acid molecules, for example. So more dilute vinegar separates more than more concentrated vinegar, for example. So to review, you need to be able to find the pH of a strong acid or a weak acid by comparing K values of water and K values of the acid, and if it's a weak acid, using an ice table, considering the important main contributors of H plus and not the other ones to make the calculations easier, and finally be able to find a percent dissociation, which is an equation that is not on your equation sheet.